Good afternoon. My name is Bob Eyrig. I'm the application engineer in the filter systems group here for Schroeder Industries. So we'll go ahead and get started here. So today's presentation a little bit different than what we typically do on a monthly basis. Typically we do a product release. In this case, we're kind of combining that with some general information on the best practices for varnish removal. So with that, the agenda for this presentation, we're going to be covering what is varnish, so we're going to define that. We're also going to talk about testing to determine if varnish is present in a system, specifically a hydraulic system, as well as practices to prevent varnish and ways to remove varnish from a system once it already exists. So, varnish, what is it? Varnish is a generic term for oil degradation byproducts, quite simply. It's, kind of want to demystify it a little bit. It's pretty much just, the byproducts of aging. And it doesn't sound like a big deal, but whenever it happens prematurely and it damages components and reduces the service life of a system's fluid and its components, it's obviously an issue. So with that, it can exist in different forms. It could be existed as a resin-like, or depending on the way in which it was formed. So what are the causes? Generally speaking, oxidation is one of the primary causes of varnish formation, and basically that is the reaction with oxygen. An analogy would be, cutting an apple. Not too long after you've cut it, you'll notice that the section of the apple that you cut will start to brown and discolor. That is a classic example of oxidation. Other than that, thermal stress due to friction or perhaps microdieseling, that's also a big source of varnish creation, as well as electrostatic discharge. We'll talk about what that is and how that's related to oil aging, as well as hydrolysis, the reaction with water. And there are other chemical reactions that can cause premature oil aging and the associated degradation byproducts. So those other chemical reactions include mixing unlike oil, as well as topping off or adding either inappropriate or too much of additive concentrations, and so on. The properties of varnish, it can appear, like I said in one of the earlier slides, it can appear in many different ways. Generally speaking, the particulate size is less than 1 micron. So in some cases, it could be even submicron. It could be 0.1 micron, perhaps. And it can also exist as an agglomerate or a conglomerate or a mass of conglomerated varnish particles. They're typically organic. They're polar, so they can dissolve in some cases with hydraulic fluid, as well as it can dissolve or be attracted onto other polar surfaces within a hydraulic system. That's why you get that lacquer type coating in certain cases in a fluid reservoir, other system components, so on. And the solubility of varnish is really based on the type of base oil, the temperature. The conglomerate formation, at least, is dependent on temperature, which, as temperature increases, the dissolving power is also directly proportional. It also increases. So if the temperature is higher, it can be more easily dissolved into a given fluid. It's also dependent on pressure. The higher the pressure, the dissolving power is less. So that's an inverse relationship with pressure. So one of the items I mentioned was base oils. So this is, I guess, part of the reason that we're hearing a lot more or getting a surge of varnish cases in the recent years because of the greater use of highly refined mineral and synthetic fluids. The more refined, the less polar or the less soluble and less conductive, which has its own set of influence on varnish formation and oil degradation. So as you can see in this table here, one of the reasons why we're seeing a surge in varnish cases is because many users are moving to Group 2 base oils, which are more refined than Group 1 base oils. And Group 2 base oils in particular contain low or no concentrations of metallic anti-wear additives, which are conductive additives, which contribute obviously to the overall conductivity of the fluid. So if those additives either are in low concentration or no concentration, that fluid, that, that the group 2 base fluid is not very conductive. So in regards to conductivity, we keep bringing that up. We'll talk about that here in just a bit whenever we discuss electrostatic discharge, but it's one of the vehicles for varnish creation. So we're tying everything together, I promise. So the effects of varnish in a system. Varnish and mineral oil, generally speaking, can lead to hydraulic malfunctions. Obviously, if we have a coating on valve spools, you can have sticking. You can create increased friction and temperature, increase the bearing wear or accelerate the bearing wear, damaged sensors and masking or blinding filter elements, reduced heat transfer as fluid is passing through an oil cooler, etc. So how do you recognize it? So like I said earlier, very small particles, at least whenever the fluid is warm, the respective fluid is warm. It can be as small as 0.1 micron or less in size. So it's very fine, and in those cases, filtration really doesn't solve any kind of problem at that particulate size because it can pass through a filter relatively easily, and it's at that size, we really can't accomplish much with conventional filtration. But as it cools down, the particulates agglomerate, become larger, become a mass, and it's a little bit more easy to approach it with mechanical filtration. Again, we'll discuss this a little bit further as far as mitigation is concerned a little bit later on. So since it's so small, we can't really see it if we were to take a sample and hold it up to light. You really can't determine if you have, varnish to the naked eye. So there are some ways to go about it. And as you can see here, these methods include testing for conductivity, testing the particulate contamination measurement at 20 degrees Celsius and 80 degrees Celsius, as well as membrane patch calorimetry. And I apologize if I botched that word. It doesn't roll off my tongue quite well, so we'll call it MPC, as well as the gravimetric test and the ruler test, or the remain useful lifetime test. We're not going to really go into the ruler test in detail here today, just because it's really a less practical measure of varnish existence because it requires special equipment, and it's based on the relative concentration of antioxidants in a given new fluid versus a used fluid of the same type to determine remaining service life of that fluid. So the MPC test is pretty straightforward. It's basically taking a sample of fluid, passing it through a fine filter membrane of 0.45 micron, and examining the shade of color of the membrane patch. That MPC value is shown here. It's kind of small, but the point is if you see where I have a line with an arrow pointing to the right, that represents an MPC value of 40. And at that point, you're talking about a critical condition that might indicate the existence of varnish. Whenever you're doing testing for the existence of varnish, you're really going to want to use, I guess the best practice would be to use a variety of methods to really confirm that varnish is an issue, other than, seeing system components that clearly have a deposit on it. You can't really tell the existence of varnish from a sample of fluid in itself. So the next way of doing this is testing for electrical conductivity. As I mentioned earlier, a lot of users have been moving more refined or even highly refined base fluids. And with that, we've seen more refined the fluid and the less conductive it tends to be, just based on the chemical makeup. And with that, for a given test fluid, if the conductivity at 20 degrees Celsius is less than 400 picosiemens, which is the unit of measure for conductivity, then the risk of electrostatic discharge is evident. So it's it's really, something that is concerning, not only because of varnish formation, but as you'll see in the coming slides, some of these voltages seen at an electrostatic discharge in hydraulic fluids can exceed 10,000 kilovolts. So it can be very dangerous and cause many different issues. Typically, electrostatic discharge or a triboelectric charge generally occurs it's not specific to a turbine lubrication system, but that's just an example, and it's a result between the friction between the fluid and the system components. In some cases, there are other more technical and scientific ways that occurs, which we can share with you privately or in another conversation. But it can be an indicator of ESD without actually seeing the fluid itself as it's being processed or being cycled through a system is an audible clicking noise coming from a reservoir or from the system. It doesn't sound quite like cavitation. There are distinct differences in the noise. And like I said, it's common to see it at a filter. It's common to see it at somewhere on a reservoir. You can see this picture of a transparent element tube with an element inside, and you can see the arcing of the electrostatic discharge within the fluid as it passes through the element. I like this chart that we have here to the bottom right. It just shows you the low conductivity of a group 2 oil versus a group 1 and a group 3. Group 3s also highly refined, and as well as group 4s, but due to the additive packages of the typical additive packages or the lack of additives that are in many group 2 base oils, the conductivity tends to be lower and therefore a higher chance of electrostatic discharge. There's a couple of images showing you the destruction of an electrostatic discharge against an element fiber. You have a breather element that's pretty much destroyed. That's the end caps and center tube. And just working through this list, it can cause holes in filter elements. It can cause uncontrolled deflagration in the tank, which are pretty much micro combustions, which can lead to fires, as well as the destruction of electronic components through the release of electromagnetic waves. So we know that there are issues with group 2s, group 3s, and group 4 base oils for a variety of reasons. One way to attack this problem, obviously, is the engineering of the hydraulic system in itself. And that's kind of where I like to start, is trying to identify whether or not a system was designed properly, or if it's possible to engineer the problem out of the system. And I guess one way of doing it is by using conductive mesh downstream of a filter, or having a conductive filter element itself. That's one way to mitigate that problem. There are also anti-static additives which can be added to a given fluid but might not be suitable for certain applications. It depends. So there are a couple different ways to mitigate the charging of the fluid and therefore eliminating or mitigating the chance of electrostatic discharge. So another method of determining whether or not varnish exists in the system is through particulate measurement or particle counting. So particle counting at 20 degrees C and 80 degrees C is a testing. I don't know necessarily in all cases if you're doing this out in the field. It needs to be done to those exact temperature specifications to have an idea if varnish could be a potential issue, but that's the standard. And basically, since the agglomeration of varnish particles is proportional to the temperature of the fluid itself, the higher the temperature, the more dissolvable and less agglomeration of those particles, and vice versa with cooler fluid. Cooler fluid, more agglomerates, and you'll get a higher particle count. So, how to reduce varnish? So after identifying that there are no engineering means to engineer the problem from the system, and generally speaking, you obviously want offline filtration, in most cases, because that's the only way you're really going to get to a given fluid cleanliness. This is kind of the next step in the process is mitigating the varnish problem through fluid conditioning. So again, offline filtration, conditioning the fluid so that obviously you're reducing the particulate contamination as much as possible, or to a required ISO cleanliness or whatever fluid cleanliness standard that you need to be at. Dewatering, of course, as I mentioned early on, hydrolysis is a cause or a potential source of premature or accelerated oil aging, as well as degassing or removing air contamination from a system, and therefore reducing oxidation of the fluid. So those are all preventative measures, if you will, to minimizing the generation of oil degradation byproducts. So this is, one way of achieving all of those conditioning points, with a vacuum dehydrator. We can dewater, degas, and have particulate filtration on one unit. So that's certainly an option for varnish mitigation applications. So once you've tested for varnish, you came to the conclusion that varnish definitely exists in the system. You have taken all the appropriate measures to condition the fluid with a vacuum dehydrator or any kind of dehydrator, as well as filtering to the required cleanliness. The next step in that process would be to actively remove the varnish from the system or condition the varnish from the fluid. With that, there's a few different ways of doing it. The methods that we'll discuss are chemical rinsing and flushing the equipment, adsorption, and instead of electrostatic purification, because we had kind of already talked about that, we'll also discuss mechanical filtration to mitigate varnish issues. So this is probably, I guess, the least practical way of dealing with existing varnish, which would be chemical cleaning and flushing, for obvious reasons. It's the chemical typically used to do this is a variation of a fluid or an additive called which is basically a solvent, and it's added to the contaminated fluid. Obviously, the concentration proportional to the amount of fluid and the fluid type, etc. Then that fluid is cycled and then ultimately disposed once the varnish that has deposited on the system components has been dissolved into the fluid. So that fluid will be disposed. Then new oil is added to the system, cycled, then discarded as well. So, like I said, it's not a very practical way of doing things, pretty expensive, and really it's not solving the problem in the long run in many cases, unless, of course, you've engineered the problem from the system and then you're just trying to clean things up. The other way of doing this is mechanical filtration. So this kind of contradicts what I said earlier, that some varnish particles are so small that they can't be filtered, and that's still true. But if the fluid is cool enough where it agglomerates and is filterable, then using fine filtration, such as the OLF series, that is a simple way of mitigating or filtering varnish from a system. The problem is, and how we're approaching this, is that, who can keep the fluid temperature at a given temperature long enough to filter the varnish out and prevent that varnish from dissolving back into solution. This is kind of where our new product release comes into play, at least for this presentation, and that is we're previewing, it's not officially introduced, but we're previewing the VEU-F unit, which is basically the MTS or the OLF series filter unit, and adding an air-cooled heat exchanger to the circuit. So this gives us a little bit more control as far as fluid cooling and helps the varnish agglomerate to the point where it can be captured and filtered out mechanically by the fine filtration. So we talked about mechanical filtration. This is the other method of approaching varnish mitigation, and that would be the adsorption method. And basically what we're doing is processing fluid through an activated or an ionic resin. And what this does is basically attracts the varnish molecules, and the varnish molecules stick to the outside of this resin. It's a permanent solution to mitigating varnish. It's also a very slow process, but we offer this kind of solution through our VMU filter units. These are very effective since it's a chemical filtration process. It's also permanent, and it can even solve, or I guess attract, dissolved varnish in the fluid. So it doesn't matter what temperature the fluid is at per se. In most circumstances, if it's really hot fluid, there might be some issues, but generally speaking, you don't have to have the varnish agglomerate or be cool to take care of the situation. And this is just a couple of images of that resin media. It's a lot finer, but as you can see, it kind of looks like the media that would be seen in, for example, a desiccant breather almost. Now this is very much zoomed in, but you can see there's spherical resin media. So we covered a lot. Of course, if you have any questions, feel free to reach out to me. And to conclude, we talked about the fact that varnish can exist in many different forms. It can be soft, it can be hard, it can be less than 0.1 micron, and so on. So there are definitely, it's not a one-size-fits-all. Oil degradation byproducts can exist in many different forms. The formation of these deposits in these byproducts increase if the temperature drops, and deposits are formed on cold points within a system, so they can agglomerate at those cooler points, as well as if pressure increases. We also talked about, how in general, the more highly refined an oil is, it's harder to keep varnish in solution, and that's why we have these deposits at different locations within a system. Sometimes hard deposits, sometimes soft deposits, and so on. We also talked about, in that same respect, that the more highly refined, the less conductive in most cases, like Group 2 oils, and that is a significant contributor to oil degradation, as well as consequences that are not usually traced to altered base oil properties, which can be expensive and usually ineffective measures that are taken, such as replacing the oil or mechanical cleaning. Well, I think under the right circumstances, mechanical cleaning, should be the first step to mitigation once it's determined varnish exists. But yes, in a lot of cases it is ineffective, and that's why we're introducing the VEU-F, where we can kind of help influence the effectiveness of mechanical filtration. And finally, and this actually was something we talked about more towards the middle of the presentation, before varnish exists, some of the steps that can be taken, of course, is through fluid conditioning in itself, and that's particulate filtration, dewatering, and degassing. For their obvious reasons, it's really kind of a domino effect as far as premature oil degradation. And with that, feel free to reach out to me at any point. I hope everybody has a good weekend, and we'll talk to everybody soon. So thank you.